This is the calculator portion of the 2003 AP practice test. So 76 says particle moves along the x-axis so that anytime t is greater than or equal to 0, its velocity is given by this v of t function. What is the acceleration of the particle at time t equals 4? The nice thing here is we have the calculator for us to find the derivative, because to get from velocity to acceleration, we should have to move one derivative down. So we can do this by hand. Cosine of u becomes negative sine of u times u prime, but maybe it's faster to just use the calculator to evaluate the derivative. So if you go to in your TI 83 or 84, you do Math 8, which you can choose the end derivative feature, and that will give you the setup to allow you to evaluate the derivative at x equals 4. So you can plug in your velocity function. Notice that as you plug in into your calculator that you're always going to use variable x in the calculator, even if there's other variables presented on paper. So we're going to ask the calculator to find the derivative of the velocity at x equals 4. So that's going to give us 1.633. So our acceleration is 1.633. For 77, we have regions A, B, and C that's enclosed between the graph and the x-axis. Keep in mind the region below the x-axis represents a negative definite integral, and regions above represents a positive definite integral. The areas of each region is positive 2, but even though the area is 2, we have negative 2 for below and positive 2 for above the x-axis. What is the value of the definite integral from negative 3 to 3 of f of x plus 1? Careful to understand that this plus 1 is under the umbrella of this definite integral. It's not just the plus 1 by itself. So the best way to make sure that we do all the operations that are required of us, let's go ahead and split this up into two problems. Go do the definite integral from negative 3 to 3 of f of x dx, and then separately I'll do the definite integral from negative 3 to 3 of 1 dx. Now with f of x dx, we can use the graph. We're just going to accumulate these values that we see in front of us. From negative 3 to 3, we just accumulate these values from negative 2 plus 2 minus 2, which gives us negative 2. And then separately, let's find the definite integral from negative 3 to 3 of 1 dx. Now this is a problem that we can do using power rule. So integral of 1 is 1x. Once we find the antiderivative, we're going to plug in our upper and lower bound. Plug 3 in for x, we get 1 times 3 is 3, minus, then we plug in the lower bound, 1 times negative 3 is negative 3, so 3 minus a negative 3, or 3 plus 3 is 6. The first definite integral produced a negative 2, the second definite integral produced a 6, so negative 2 plus 6 equals 4. For 78, it says the radius of a circle is increasing at a constant rate of 0.2 meters per second. What is the rate of increase in the area of the circle when the circumference is 20 pi meters? This is a related rates problem. We have time that is underlying all these, that's underlying these the units of these problems here. So let's see, we have two formulas that stand out. We're dealing with area of a circle, and we're also dealing with the circumference of a circle. Area of a circle is pi r squared, circumference of a circle is 2 pi r. We can gather some information from what the problem tells us. The radius is increasing at a constant rate of 0.2 meters per second. So radius of a circle, that's r, but it's increasing, so we know it's going to be a rate, so this must be talking about dr dt. So dr dt is increasing, which means it must be positive. So dr dt is 0.2 meters per second. Okay. What is the rate of increase in the area of the circle? We want to know about the area of a circle, but not just the area, it's the rate of increase of area. So we want that to be a dA dt. We're looking for dA dt when the circumference is 20 pi meters. Okay, so these are the information that's provided, and this is indication of what we're trying to look for, what we're trying to solve for. Okay, so we have our area and circumference equations. I'm going to go ahead and find the derivative of each of them with respect to time. So a becomes dA dt. Pi r squared, we can apply power rule. Remember, pi is just a constant here. It's not a variable, so there's no need for a product rule. So we do power rule here, 2 pi r, but every variable gets affected by time, so we need to apply dr dt. For circumference, I don't know if I need it here, but I'm going to go ahead and find the derivative for circumference. C becomes dc dt. 2 pi r becomes 2 pi. R disappears, but it produces a dr dt. Okay, so we'll see if we need both these equations. Well, I want to find dA dt, so I know I definitely want to use this. So dA dt is 2 pi r dr dt. We have dr dt, right? That's provided in the problem, so we can plug 0.2 in for dr dt. Now the missing information is this r, this radius. And we don't have radius provided for us explicitly, but we do have something related that can help us get there. We have circumference is 20 pi, and we know circumference formula is 2 pi r. So if I do 2 pi r is equal to 20 pi, I can solve for r, and if I divide both sides by 2 pi, 20 pi divided by 2 pi equals 10. So radius is 10. So if r is 10, I have now enough information to find dA dt. So I have 2 pi times 10 times 0.2. Multiply this together. If I want to keep that pi, I get 4 pi square meters per second, and that matches the answer choice for C. Okay, 79. For which of the following does the limit of our function exist as x approaches 4? Okay, limit exists if the graph approaches the same y value from both sides of x equals 4. So for this one, we see the limit does exist because if I choose a point to the left of 4 and if I move towards 4, and if I choose a point on the other side of 4 and move towards 4, notice that both these arrows are moving towards the same y value. So there's a consistency there. We know that the limit exists. Even though the point is defined elsewhere, we're looking at the path of the graph. The path of the graph is consistently moving towards that hole. The point does not have to exist for the limit to exist as long as the graph is moving towards the same y value. Now here, second one, if I choose points close to 4 on either side, and if I move towards 4, notice how the arrows are moving towards the same y value. So again, the limit does exist. Now for this one, the limit does not exist because if I choose a point on the left side of 4 and use an arrow to indicate moving towards 4 on the graph, and if I choose a point on the other side of 4 and indicate with an arrow, you see that these arrows, they don't move towards the same y value, right? One arrow is moving towards a y value of 4, the other is moving towards a y value of 2. They don't approach the same y value, so therefore the limit does not exist. For graph 3, just graphs 1 and 2. Okay, number 80. The function f is continuous from -2 to 1 and differentiable from -2 to 1. So no breaks in the graph and smooth curve all the way through. We have some ordered pairs that's provided for us. Which of the following statement could be false? So I just sketched the graph to have something visual to work off of. So I know my graph is smooth and continuous and differentiable, and I'm just making it go through the order pairs of -2, -5, and 1, 4. Okay, so let's look at each of the options here. There exists a c between -2 and 1 such that f of c is equal to 0. So f of c equal to 0 means that the graph has to cross the x-axis at some point, right? The y value has to be equal to 0. And this is true because we know the graph is continuous and differentiable. We start off at a point below the x-axis and we end up at a point above the x-axis. So the graph has to connect through the x-axis at some point. So we call that's true by intermediate value theorem. So intermediate value theorem says if I have a point below my target and a point above my target, it has to cross through that target y value somewhere in between if we can guarantee it's continuous, and that is stated in the problem. Okay, let me come back to part B here. So C, it says there exists a point such that f of C is equal to 3. Again, this is an IVT problem, intermediate value theorem problem. Can we guarantee that the graph is going to cross a y value of 3? And the answer is yes, because again, we start off at a point below our target y value of 3, and we end up at a point that is above our target y value of 3. So if we're going from negative 5 to positive 4, it has to cross a positive 3 somewhere between. Okay. Option choice D is, is there a point such that f prime of C is equal to 3? Can we guarantee a slope of 3? If the graph is continuous and differentiable, that means whatever slope exists between the endpoints, there has to be that slope on the curve as well. So this could be applying mean value theorem. But let's see if we can guarantee a slope of 3. We have two endpoints, so if we can figure out the slope of these two endpoints, then whatever that slope is, it must exist somewhere between the 2 points. So if I take those two order pairs and do change in y over change in x, 4 minus negative 5 divided by 1 minus negative 2, I get 9 over 3, which is 3. So the slope between the endpoints is 3, so there must be a specific slope of 3 somewhere between negative 2 and 1, and so we know option D is also true. Okay. There exists a C between negative 2 and 1 such that f of C is greater than or equal to f of x for all on the closed interval. So what this is saying, this is kind of an extreme value theorem where no matter what point I choose, or whatever point is on f of x, I can always find a point that is greater or the same as that point. So if I choose f of 1 is equal to 4, I can say f of 1 is greater than or equal to 4 as well. So any point has to be greater than or equal to any point on this f of x. So back to option B here. This is the one that we can't guarantee, where there's a slope of 0. We can't guarantee a slope of 0 unless Rolle's theorem passes. And the conditions for Rolle's theorem do not all pass. There is continuity, and there is differentiability, but the two endpoints are not the same. So if the endpoints do not share the same y value, we can't guarantee a slope of 0, and that's one of the conditions for Rolle's theorem. Okay, for 81, f prime is equal to sine of x squared plus 1. How many relative extrema does our function have? If we're looking at an f prime graph, relative extrema is where the f prime crosses over the x-axis. So it has to cross from negative to positive or from positive to negative. So I put this in the calculator, into the graphing calculator, and sketched it and see what f prime graph gave me. So it's hard to see here, so I'm going to zoom in a little bit here. If you look at this graph here, it crosses past through the x-axis 4 times. So we know that at each of these points, there's going to be a relative max or relative min.